So in this first problem, we have two painters carrying some plywood, has a mast to it, and there's a paint can, and both painters are holding the can up. And we want to find out what is the force that each person is pushing on that paint can or up on the plywood with. So person A has a force putting up, that's force A. FB is the B person pushing up. The paint can has a weight, so F paint can. And the piece of plywood has a weight, so call this F wood. So if we know that we're in static equilibrium, the net force has to be zero, right? So the sigma, the sum of our forces equals zero, which equals FA plus FB minus F wood minus F paint. So we first start by writing out some of our forces. Then we look at our torques. I'm going to make A my hinge point, so I'm going to base everything off of A. So when we base everything off of A, and say the sum of our torques, all right, and they all again have to equal zero. So equals zero. So now let's talk about the torques that we have. Well, FA can't produce any torque on itself because its distance, its radius would be zero. Remember, torque is radius times force. If we were to jump all the way to painter B, we find out that painter B is 2 meters from painter A. So that's going to be plus 2 times the force of painter B. And then minus, so the plywood has a weight of 100 newtons, and it's in the middle of the piece of wood. So the wood is 3 meters long, so right in the middle would be 1.5 times 100. And then minus, right, the paint can on the top says a paint can with a weight of 30 newtons, and the paint can is 1 meter from position A, so 1 times 30. So if we look at this, we can rewrite this torque equation as 2B equals, and if we bring both terms to the other side, and they were going to become positive on the other side, 180. We solve for B, and the force of person B is 90 newtons. Well, if we know the force of person B, we can plug that back in to this equation up here, and now we can find out A. So 0 equals FA plus 90, and then minus the wood, which was 100, and minus the paint can, which was 30. So 0 equals FA minus, we do all this math, minus 40. So FA equals 40 newtons. So that's number 1. Okay, let's look at number 2. So in this picture, our people, they're balanced off of that man's arm. We're given the woman's weight at her center of mass CM is 0.3 meters from the fulcrum, right? So like somewhere here. And then the man's center mass is 0.1 meters from the fulcrum. So his is like somewhere here. I want to know how much force does the earth push back up on the two people with. So again, if we draw our diagram, change the color here. So F, this is the woman's weight. This is the man's force pushing down. And then the earth right here is going to push back up. So, you know, the net force, F net, is 0. And that's going to be FW plus FM. I'm sorry, I'm going to write this backwards. Or I'm writing this backwards. F net equals 0. And then we're going to do FE minus FW minus FM. Because the earth is going up and both of the woman and man's weight are pulling down. So for our hinge point, I'm actually going to make this my hinge point, which we're definitely allowed to do. There's nothing wrong with that. So if I make that my hinge point, I know the net torque has to be 0. So On the left-hand side, we have the woman's weight, which is 500, and her center of mass is 0.3 meters from the fulcrum. So we're going to have 500 times 0.3, and the man center of mass is 0.1 meters, and his weight we don't know, so we have plus 0.1 times Fm. Right. In this problem, because we changed our axis of rotation to here, and now it's in the middle, we actually don't add these two. We have to subtract them because they are trying to rotate the object or the system in opposite directions. So this is a minus sign because the woman is actually trying to rotate the system counterclockwise, which is positive. The man is trying to rotate the system clockwise, which happens to be negative, and that's why we subtract them. So we can rearrange this and solve for Fm. All right. So we have 0.1 Fm equals 150, or the force that the man has is 1500 newtons. And then if we plug all of this into the F net equation, the force of the earth minus the force of the woman, well, her weight is 500, minus 1500 equals 0, or the earth pushes back up with a force of 2000 newtons. So those are the two static equilibrium problems, right? We drew a fluid body diagram, we added our torques, we chose our axis of rotation, and then we substituted and solved. All right, so let's look at some moments of inertia questions. So number one, Jasmine spins a fan with a radius of 0.5 meters by applying a force of 3.5 newtons on the end of the fan blades. The span has a moment of inertia of 0.22 kilogram meters per squared. What is the angular acceleration of the blades? So here's what we know. We got radius is 0.5. The force is 3.5. I is 0.22. And we are looking for alpha. So in order to find alpha, we would use torque equals I alpha. We are given I, that's 0.22, but we would need to first find torque. Well, torque is R times F. It's going to be 0.5 times 3.5. So the torque being applied in this problem is 1.75 newtons. And then once we know the torque and we know I, we can solve for alpha. So we'll put the 1.75 up here equals I alpha. If we solve for alpha, we divide both sides by 0.22, and we get 7.95 radians per second squared. So two, a solid disc has a radius of 0.15 meters. It's mounted on an axle that's perpendicular to the circle at the end of the disc in the center. Olivia applies a 45 Newton force tangentially to the disc and acquires an angular acceleration of 122 radians per second squared. What is the mass of the disc? All right, so we're trying to find m. So this one we're going to work backwards on here. So here's what we know. We know the radius is 0.15 meters. We know the force is 45 newtons. And we know alpha is 120 rads per second squared. We're trying to find out m. Well, with R, F, and alpha, we're going to use T equals I alpha to start. So our torque is 0.15 times 45. So I'm just going to write it as 0.15 times 45 equals I times alpha. And we know alpha is 120 radians per second squared. So I'm just going to determine what is the mathematical value for our moment of inertia. So 0.15 times 45 divided by 120. Our moment of inertia is 0.056 kilogram meters squared. And from this, we are given the formula for I. So 0.056 equals 1/2 m times r squared. Well, our radius is 0.15. So now if we work backwards again and we solve for m, we can divide both sides by 0.5 and divide both sides by 0.15 squared. And the object has a mass of 5 kilograms. All right, question 3. We have this solid disk with a mass of 24.3 kilograms, and it's got a radius of 0.314 meters. It's free to rotate about a frictionless axle. Where 2 forces are applied to it, perpendicular to the disk, what is the net torque produced by the 2 forces and the angular acceleration of the disk? So because we have 2 forces being applied to the object, they're going to both produce a torque because they're both being applied perpendicular to the axis, and they're going in opposite directions. So torque equals force times radius. Now, this object is having its force applied above and below the axis of rotation at the same distance, right? It's both times the radius is the same. So we can ignore r for a second. So the net torque is just the difference in the 2 forces, which would be 35 newtons, because 125 minus 90 is 35. And then we can multiply that by 0.314, and that's going to tell us our net torque. Right? If they were being pulled from different distances, then we couldn't do it as easily as this, but in this case we can. It's 10.99. It's going to make this 11. So 11 Newton meters. So that's our torque. B, what's the angular acceleration of the disk? All right, so now let's find the angular acceleration. So torque equals I alpha. 11 equals, the formula for I in this problem is 1/2 mr squared. So I'm going to write for I 1/2 24.3 m. R squared is 0.314 squared, and then that equals alpha. So we've got alpha. So we're just going to perform some simple algebra. Divide both sides by half, by 24.3, and by 0.314 squared. And I got 9.18 meters per second squared. All right, last question on this sheet. We have this rotating door made of 4 rectangular sections as indicated in the drawing. The mass of each section is 85 kilograms. The person pushes on the outer edge of one section with a force of 68 newtons that is perpendicular to that section. What is the magnitude of the door's angular acceleration? So T equals I alpha. So if we want to start with that, here's what we know. We know the mass is 85 kilograms, and we know that the force is 68 newtons. We're given the length. It's 1.2 meters. And again, we are trying to find out alpha. So the torque being applied in this question is going to be 68 newtons. And since it's being applied at the very outside of the door, the length of the door is also the radius, 1.2, equals, we have to calculate I. I is 1/3 mass. So the mass is, the whole object is rotating. It's not just the single door. So the mass is 85 times 4, and then times the length 1.2 squared, and then multiplied by alpha. So we found the torque. It's force times radius as always. Because it's being pushed at the outside of the door, the radius happens to be the length of the door. We then make sure we multiply our mass by 4 because each section is 85 kilograms and the whole thing is rotating. And then we just work to solve for alpha, and alpha is 0.5 radians per second squared.